Chapter 7, slides 26 to 40. We're now going to look at substitution nucleophilic first-order reactions. We're going to try to understand how these reactions differ from second-order reactions. First order. Okay, I've set up the flashcard for you, and you might notice a few differences, but also a few similarities from what we just covered in SN2. In SN1, you'll notice that the nucleophile looks a little different. It's not formally charged per se. That's one of the things that we're going to see as a major difference. We'll get to how to figure out the competition. Like, when do I apply SN1? When do I apply SN2? Because it can be a little confusing, but we'll get to that. Let's first start with how SN1 differs from SN2 from a mechanistic standpoint. I'll start with the same structure as I did for SN2. Notice again that we're using an alkyl halide. So alkyl halides are a requirement, or at least a good leaving group is a requirement for these SN1 and SN2 reactions. So I still have a good leaving group. I still have that dipole, right? Because that carbon is partially positive, the bromine's partially negative. So I've set myself up for some chemistry. I got a good leaving group, I've got the dipole. And the first step that I'm going to do in an SN1 is called solvolysis, or leaving group leaves. Solvolysis is really a fancy term for the leaving group leaving. And we'll talk a little bit more about that later, but effectively, you've seen this before. The solvent, the water, which is polar protic, surrounds the electronegative bromine and helps carry it away. So we're going to see the leaving group leave, take the electrons with it. What we're seeing here is a stepwise mechanism. When that leaving group leaves, what happens? The bromine leaves, right, surrounded by the solvent, carried away. And what's left behind, if that leaving group leaves, is a carbocation. So we started with an sp3 alkyl halide, because that was, our necessity to do these types of substitution reactions. And we're now at a point where we formed a carbocation. This is an intermediate. So step one, leaving group leaves, forming this intermediate. It's a carbocation. I now have an sp2 trigonal planar carbon. And this is always going to be our first step, right? The second step, which I should do, but I'm not going to show you right now because we'll get to it, is a stop sign. We're going to check for possible rearrangements. They happen sometimes, not all the time. So the second step is check for rearrangements. I'm going to tell you right now, there are none. Okay, for this particular example, there are no rearrangements. So let's move forward. The last step, okay, so first step, leaving group leaves, form an intermediate, sp2 trigonal planar carbocation. And the last step is the solvent, which there's a lot of it. Man, there's a lot of that solvent. And it is also less greedy than the bromine, because it's oxygen, not bromine. That oxygen is going to make a bond with that carbocation. But remember, it's flat. It could happen from the front, or it could happen from the back. This is very similar to what we saw with those radical reactions. So we could get, I'll write it down here. We could get attack from the front, or attack from the back. So the water substitutes out for the bromine ultimately when you stand back and look at the whole reaction. And we've just highlighted this front or backside attack due to the flat nature of the carbocation. And for this particular case, we don't want to end with these positively charged oxygens. So what you're going to start seeing is for certain reactions, when the final product has too many protons, too many hydrogens, or it has too few, we do a workup. And the workup is simply just to get everything back to neutral. In this case, I have too many protons on the oxygen. What removes protons? Who takes protons or hydrogens off? If you said bases, you're correct. So you're going to work it up under mildly basic media. Maybe you'd throw in just a little bit of sodium bicarbonate to try and neutralize everything. And so your product distribution at the end is going to be, the final answers are going to be these alcohols in a 50-50 ratio, front or backside attack. Right? So the base is simply going to remove the extra proton, giving the oxygen its electrons back. That's the acid base. This is your acid base workup. AB, I'll be using, whenever I do an acid base mechanism, I'll be putting it or labeling it as AB. So now we have a mixture. In this particular case, this is the mixture we get. What's the relationship of these two products? What's the relationship of these two products? Well, they are enantiomers. And if I have a 50-50 mixture of enantiomers, this gives me a racemic mixture. Now, students are always looking for trends. Does SN1 always give you a racemic mixture? No. Sometimes it gives you one product. Sometimes it gives you a mixture of diastereomers. Sometimes, like in this case, it gives you a mixture of enantiomers. Please understand that you need to learn the SN1 mechanism. You apply it to your system. You predict the products, and then you can step back and look at the relationship of those products, just like we did with radical chemistry. Let's look at the rate. For a reaction like this, the rate is K times the concentration of the electrophile to the first order, hence SN1. Now, just remind you that the alkyl halide in this case is our electrophile and the water was the nucleophile. So the rate was determined experimentally, and I'm giving it to you. And this is also telling because we know that the starting material starts, at some energy. And I am telling you that adding the nucleophile in that second step does not change the rate. So when they were running these types of reactions, they increased the concentration of the nucleophile and the rate stayed still. Why? Because the first step in making your carbocation intermediate is the rate determining step. I'll just write the product there. So the first step is rate determining. From starting material to intermediate, the nucleophile played 0 role, right? From starting material to intermediate, it was simply the leaving group leaving. That's the only mechanistic thing that happened from start to intermediate. The nucleophile doesn't play a role until the second step when it gets to the product. So therefore, since the rate determining step is the first one and doesn't include the nucleophile, the concentration of the nucleophile plays no role. Only when you increase the concentration of the electrophile do you start to see changes in the rate. How does this reflect when you're doing an ASL? So in ASL, we can actually have a model using our hands to portray this entire mechanism. I also want you to note I call it the squiggle line, right? So we have wedge, we have hash, and we have squiggle. That's not a mistake. Squiggle lines are a shorthand way of saying both front and back at the same time. I just wanted to point that little way of writing it out. Okay, what about stereochemistry? We saw implications that there were stereochemical changes when we did SN2. How about SN1? Well, similarly, if we started with a molecule that was chiral, and we have the bromine 1 and the ethyl 2 and the methyl 3 and the hydrogen 4. Oh, look, the hydrogen's in the back. Perfect. So when I go from 1 to 2 to 3, that is turning my car right. So that's R2-bromobutane. If I were applying SN1, the leaving group would leave. So let's review. This R2-bromobutane has a chiral center. All right, so this is an sp3 tetrahedral, chiral center R. If the leaving group leaves, if the bromine leaves, we're going to form a carbocation. So we're going to form a trigonal planar carbocation. This is sp2 hybridized, right? Carbocation intermediate. And it's trigonal planar. It's flat. We saw that with the hands. Maybe it doesn't look so great with, let me bring my hydrogen down a little bit here. There, that's a little bit better. So when the water now in the second step, so this being the carbocation intermediate, in the second step, the water attacks, I have equal opportunity to attack from one lobe or from the other, front or backside attack. Now, I just want to point out, if you spent some good money buying a chiral R2-bromobutane, right? You're like, I'm just going to buy R. That's going to, cost a little bit more because it's pristinely pure and enantiomerically. And then you go and say, all right, I'm going to do an SN1 reaction. Well, you should have saved your money because you're turning your chiral center, your stereocenter, sp3, into sp2. You've completely destroyed your stereocenter in the process of SN1, right? And that happens when the leaving group leaves and you form that carbocation. You've completely destroyed your stereocenter. So then, if the water comes in from the front, ultimately we will get the OH, the ethyl, the hydrogen, and the methyl. And if OH came in from the other side, we get these. Put these, a mixture of these two compounds. Now let's figure out their relative stereochemistry. In the top case, oxygen is 1, ethyl is 2, methyl is 3, hydrogen is 4. Ooh, hydrogen is in the back. So if I go 1 to 2 to 3, the top one is S. The bottom one, oxygen is 1, ethyl is 2, methyl is 3, hydrogen is 4. Oh, hydrogen is in the back. Great. 1 to 2 to 3, R. We have just made a mixture of enantiomers. So you can see a little bit about the effects that different mechanisms have on stereochemistry, right? For this case, we ended up with a mixture of enantiomers. In SN2, we would have just gotten one inverted product. But I want you to not memorize the fact that, oh, I get enantiomers. No. I could give you a different starting material, and after undergoing an SN1 reaction, you might end up with one product. I could give you an SN1 reaction with the starting material, and you could end up with a mixture of diastereomers. So don't try to memorize a trend of products. Understand you need to learn the mechanism, and each case is a new problem to solve, okay? And you could get something different product-wise in the end. So don't try to figure out all the permutations. Learn the series of steps, do the protocol, and apply it and figure out what you get. Okay, I'm going to take a moment now to talk about those rearrangements that I skipped over when I went over the mechanism. That is the stop sign in the second step, right? First, you do solvolysis, leaving group leaves. Well, let's do that. In this first step, the bromine is going to leave. Now notice that our bromine is at a stereocenter, but we're going to destroy that stereocenter because the bromine leaves. We turn that molecule into a carbocation in our first step. Okay, done. We just did solvolysis. We formed our carbocation, check. All right, then there's this second step. This is the second step you should consider. So first step is leaving group leaves, solvolysis. Second step, stop sign. This is where you apply the things that we learned in the chapter 6 for radical chemistry. Now remember, we've got a carbocation. This is a carbon that does not have an octet, okay? It's lacking electron density. Do you remember the things you ought to look for to stabilize carbocations and radicals? What trends did we discover in understanding the stability of empty carbons? Well, we looked for inductive effects and we looked for resonance. I'm going to focus on the inductive effects. Tell me about this carbocation. Is it primary, secondary, or tertiary? If you said secondary, you would be correct. It has 2 carbons on either side of it. Okay, we could do better. Given the structure I've just drawn, there's a position right next door that, man, if only that carbocation could be tertiary. There's a possibility, right? So if you look, the carbon next door, wouldn't it be nice if the carbocation could be there? So it's important to understand what is there. Look at that tetrahedral carbon next door. That tetrahedral carbon has 2 carbons and a hydrogen. I want to keep the carbons there, okay? What I want to do is simply perform a hydride shift. What is a hydride? Okay, well, I'm going to take a moment to describe those over here on the side. Okay, H2 is how hydrogen diatomically exists in nature, right? This is the gas diatomic hydrogen, H2. H plus is it's called a proton, right? H plus is an acid, but H plus, if you think about it, how many electrons does H plus have? 0, right? It has 0 electrons, and so we call it a proton because the only thing that it's made up of is 1 proton in the nucleus. H minus, or a hydrogen with a lone pair, is called a hydride because it has a lone pair, 2 electrons. So these are the various forms of hydrogen, H plus and H minus, a hydride. So what this means for us is that the hydrogen next door wants to pick up its electrons in the bond. So it's behaving like a hydride because it's the hydrogen with those 2 electrons. I always imagine that the carbocation represents an empty seat, right? It's an empty orbital. It's my empty seat at the table. And that hydride unplugs its electrons and hops over to the empty seat. So the hydrogen and its 2 electrons unplug from that carbon, that tertiary carbon, and hop over, a hydride shift. Now where's the empty seat? The empty seat is now at the tertiary position. Voila! Woo! We are done. We've actually lowered the energy of our intermediate. So if we were going to map this out in an energy diagram, you would have the starting material, rate determining step to the high energy carbocation, the secondary one, but then it would cascade a little bit down to still a high energy carbocation, but lower in energy than the first one. So there's 2 intermediates here, and then it finally goes to the product. Okay, so then we would continue on, but I'm not going to finish this one out. Front and backside attack of the water at that carbocation. But the key here is that we actually made a more stable carbocation. Sometimes, however, a hydride doesn't exist next door, or a hydrogen doesn't exist next door, and so we do the next best thing, which is an alkyl shift. We begin with the leaving group leaving, first step. First step is solvolysis. Okay, so now what I have is the carbocation at the secondary position. Not bad. Secondary isn't terrible, but man, if I could be tertiary, I'd be so much more stable. So we look next door and we see that the carbon next door has a lot of alkyl groups. That's a quaternary carbon. It's got 4 carbons around it. So if only we could move the hole over there. Well, in order to do that, we have to use one of those to fill the hole at the secondary position. So there's no hydrogen. Like there was in the previous case, there isn't a hydrogen. I look for an easy hydride shift. There isn't one. Okay, so in this case, doesn't matter which one, I'm going to do an alkyl shift. So it's a methyl group that is going to unplug from its current position, and it's going to shift over and fill the hole. So again, it's like at a dinner table, right? There's an empty seat next to you. If you pick up your silverware and your water glass, because maybe you used it, and then you hop over to the empty chair, there's a new empty chair. It's exactly where you just were. Sometimes I'll note rearrangements can be drawn with a swirly arrow. That's a rearrangement arrow where it's a swirl. So something happened that's kind of nuts. Now that's the product of my shift, of that alkyl shift, the methyl group hopping over, and now the hole is where I once was, where the alkyl group was. Now I've gone from secondary to tertiary again. Ooh, again, the energy diagram looks like the one I just drew above, with 2 carbocation intermediates, the second one being lower in energy than the first. That's a plus. You can only do carbocation shifts once, so don't try to shift and shift and shift and turn your carbocation from one end of the molecule to the other. You can only really shift it time-wise once, so it's sort of a one and done card. If there isn't an immediate benefit to shifting, it's not going to happen. Let's look back up to our first case here. Notice that when we looked at our carbocation, it was a secondary carbocation. If I look left, right, if I look at shifting it to the left, that would have been a primary. And if I shift it to the right, it would be secondary again. There's no beneficial reason to shift in the case that I gave you in the first one. That's why I said stop, look around, but you had to trust me at this point that there was no rearrangement. So in that case, I gave you one where there's no reason, no thermodynamic stability reason to change its position. Okay, so once you're done, once you've done your one and done, you spent your coupon, you finish the reaction out, right, with the nucleophile attacking, and you move on. Okay, so I won't finish these out for you, but I just wanted to show you what a hydride shift is and an alkyl shift. I always look for the hydride shift first, and then if I can't find a hydride at that position, then I shift over an alkyl. All right, so let's go over a few things trend-wise that we see for SN1 as we did with SN2. What are we looking for in the structure of the alkyl halide? And remember, the alkyl halide is our electrophile. Well, as you notice, because we're forming a carbocation, it makes the things that we're looking for trend-wise in the alkyl halide or electrophile a little different or a lot different than the SN2 reaction. In the SN2 reaction, recall that it was all about stereochemical. Because you had to shoot in, the nucleophile had to shoot in at an sp3 carbon, you had to make sure there was space to get in there. We don't have to worry about that for SN2. Sorry, for SN1. Why? Why don't we have to worry about that for SN1? Well, the reason is because we kind of open things up by changing it from a very tight sp3 tetrahedral. When the leaving group leaves, we end up creating this very flat species with a lot of open space. So space is not an issue for SN1. What is an issue for SN1 is substitution patterns or inductive effects. Because I'm forming an octetless carbon, right, the carbocation, it's all about that rate determining step in making the carbocation. So I've really got to think about stability. So what you see is actually the opposite of SN2. A methyl is the worst case scenario because when that leaving group leaves, that carbon has no inductive stabilization. There's no hyperconjugation with those extra carbons next door. A primary is only slightly better, but man, I'm shooting for gold here. I want tertiary. Tertiary systems, tertiary alkyl halides are the ones that have the leaving group leave, and what's left behind is a very stable carbocation with inductively electron donating groups around me with their large electron dense clouds hovering over my empty p orbital. So we see the reverse trend for the alkyl halide, and the trend observed is due to induction, right? Or hyperconjugation. We want more and more electron donating groups because remember, alkyl groups of any variety, methyls, ethyls, butyls, they are electron donors. They're little balls of tetrahedral clouds. And the more of those clouds you have around your emptiness, the better you feel. We saw this. This is a retrieval cue from chapter 6 notes. Remember, I had this exact slide in those notes, except we also had it for radicals. It's the same trend for radical stability as it is for carbocation stability. Tertiary is better than having resonance. This is resonance, lots of resonance, which is about the same as resonance, which is about the same as a secondary. So this is a primary carbon with resonance. And so that's about equivalent to secondary, but notice that tertiary beats even resonance. Wow, that's kind of cool. And then secondary is better than primary, is better than a methyl. And we don't even want to talk about vinyl. Vinyl is a no-go. It's so unstable that we'd never see alkyl halides undergo SN1 that are vinyl. That's why I was having you highlight the alkyl halides and not the vinyl halides, because you can just exclude vinyl halides from undergoing this chemistry. What about leaving groups? Are there leaving group trends? Luckily for us, they're the same trends we saw for SN2. Iodide is a better leaving group than bromine, is a better leaving group than chlorine, is a way better leaving group than fluorine. So we're not even going to talk about fluorine as a leaving group. It's just not really realistic. We're going to concentrate on iodine, bromine, and chlorine, and it's the same trends, right? Iodine, I- is a better leaving group than bromine. is a better leaving group than chlorine. Same leaving group trends. Why? Well, when they leave as I minus or Br minus or Cl minus. And when you're just looking at the leaving group itself, it's the same trend, right? A leaving group is a good leaving group. Why is it a good leaving group? Because when it leaves, it's stable. A leaving group is only going to want to go if the charge it takes with it, the negative charge in this case, is a stable effect. So a good leaving group is a good leaving group is a good leaving group, and we can think about REO, because a leaving group usually takes its electrons with it and thus is a negatively charged species, and we can use REO to figure that out. So REO is good for determining stability of conjugate bases. That's what we were doing in that chapter. REO is also good for determining the leaving group ability, because a leaving group will only leave if it's stable. It's not gonna, something's not gonna leave a molecule if it's gonna cause this massively high energy negative charge. Like, what's the point? What's the thermodynamic thrust for it? It's only gonna leave if it's a pretty decent leaving group, which means just like a conjugate base getting released, the reaction only goes in that direction if the conjugate base is stable. It's the same type of thought process. In one case, you're looking and you're analyzing the negative charge left behind, and in leaving groups, you're analyzing the negative charge left behind on the leaving group atom. Understand that if a leaving group is stable, then it is not a strong base. It's not going to be good at coming back and reacting. It's fine. It's stable. I've left. I'm actually good with my negative charge. So they don't tend to be good bases, right? Which is good for us because it's not going to go out and do some wayward chemistry we don't want it to do. How about the reactivity of the nucleophile and the concentration of the nucleophile? Well, as I mentioned before, the rate for an SN1 is only dependent upon one thing, and that is the concentration of the electrophile. So the nucleophile plays no role in the rate of this reaction for SN1. And again, we have our starting material, the leaving group leaves, you form a carbocation, the nucleophile plays no role here, and then you end up with the product. And this is the only part where the nucleophile comes in. But since it's not the rate determining step, it doesn't play a role in the rate. You can, same thing with the reactivity. Like, oh, what if you made the nucleophile stronger? Nope, not going to play a role. Like, you can increase the concentration of the nucleophile. It won't do anything for the rate. You can bump up its reactivity and make it a stronger nucleophile. Nope, not going to bump up the reactivity or rate of the reactivity. Again, it's only the electrophile that's doing much in the rate determining step. All right, what about solvent effects? Okay, well, we're dealing with a different beast here, and I want to relate it back to SN2 chemistry. Now, think about it this way, right? When I was talking about my party effects, okay, there's a party. You have a partial positive and a partial negative atom, and they go to a party and they're attracted to each other, but they go home alone, no reaction. That's general, okay? What if you have a partially positive electrophile and you have a strong nucleophile, formal negative charge? Then there's going to be a reaction, okay? And we saw this. That's called SN2. The nucleophile was the strong one, the formal negative charge. And they were both very attracted to each other, but at least one of them was bold enough to ask the other one out. Let's think about what we're seeing with SN1. Remember, the leaving group leaves and you form a carbocation. an actual formal carbon plus. The nucleophile stays weak, partially negative, right? The oxygen was just partially negative. It wasn't OH minus, it was just a partially negative species, which also served double duty as our solvent. And so our charge in this case was the positive. And so SN1 is the opposite scenario. We get a reaction, but we did it under reverse charged conditions, okay? So remember that in SN2, the solvent could surround the negative charge and stop it from doing what it wants to do, right? But remember, understand that a negative charge is an excess of electron density. The role of that negative species is to go out and react, right? That's Rocky, who wants to find his girlfriend and can't do it through the crowd, right? The difference here in SN1 is that solvent plays a good role. It's not a detriment. In fact, a carbocation, the positive charge, is empty. And so when you're feeling empty, what do you need? Maybe you need a group hug, okay? Maybe you need a whole lot of love, even if you didn't want it. You need that group hug to make you feel better, to make you feel more stable, right? So I think about a cartoon with like SpongeBob and Squidward getting a group hug from all of his friends. It's like you're empty. And what's going to make you feel more stable is that group hug. So the solvent will act as your friends in this case, surrounding you and stabilizing you. So not only is the solvent helping to stabilize, and you can see that here, where the solvent, remember we called it solvolysis. The solvent with the leaving group, here's your leaving group bromine. You want to carry that bromine away and make sure it feels okay in getting carried away. So the water, the positive parts of the water, the protic part, will associate with that Br minus, helping additionally. I mean, Br minus is fine on its own, but now with water surrounding it, it's feeling a lot better, and that gets carried away. And then the carbocation left behind, your empty hole, man, it's wishing that it had some friends around, and the water can serve double duty there because the partially negative end of the oxygen, or of the water, surrounds that empty carbocation and helps to stabilize it. So the stronger the dipole of the solvent, the better this effect is. And so solvolysis is the carrying away of the leaving group, but it's also the stabilizing of the carbocation as a group hug, making it feel a little bit better. You know, we're here, we got you. And then think about it. Who's reacting in this next case? Who's going to interact and form a bond with that positive charge? Well, the solvent, it's right there. It's both stabilizing and then it just reacts. The oxygen can't help it to make a bond and really make it feel better. So now we're going to look at one alternative for a leaving group. So I'm kind of sidestepping here. I know this whole chapter is about alkyl halides, but I want to show you that you can do some SN1 chemistry with something other than an alkyl halide. Consider using an OH as a leaving group. Now, on its own, OH is not the greatest leaving group, right? It's not as stable as an iodine or a bromine or a chlorine minus. OH minus is not as stable, right? So it would be I minus is way better than bromine minus, which is way better than chlorine minus, which is way better than OH minus. So on a scale of leaving groups, OH minus is not a great leaving group. However, I can make OH into a better leaving group by adding acid. So I could add HCl or H2SO4, okay? Notice that I'm still doing this in water. So HCl, so I've got an acid here. And what's going to happen is that the OH does acid-base chemistry first. So if you have an OH with acid and you want to do an SN1, we're going to add a step. Step 1A is acid-base chemistry. This is converting my OH into a better leaving group. So the OH is going to react as the base, and it just put on an extra proton, right? HSO4 minus is a pretty stable conjugate base. If it's a stable conjugate base, it's not a strong base. So that goes away. So step 1A was acid-base chemistry. Now I have a good leaving group. It's called water. The leaving group is not going to leave as a negative charge anymore. It's going to leave as H2O neutral. That's a great leaving group, right? Because right now it's charged, and if it leaves, it's just going to be water. So I've created OH into a better leaving group by adding acid. Acid-base mechanism first. And now step 1B is solvolysis, or leaving group leaves. Okay, so my leaving group is going to leave. Now I have okay. Now in this case, this is kind of a silly reaction. I should probably make this a little bit more interesting by changing these to ethanol. Let's change these to something interesting, maybe methanol or ethanol. Why? Because if water leaves and then the solvent's water, water's just going to add back in, except you're going to scramble your center. So that would have been kind of a ridiculous question. At this point, I've gotten my carbocation. Next step, stop. Stop sign. Look around. I've got a secondary carbocation. Can I do any better? Well, I could. Check that out. If the carbocation through a hydride shift hops over to either side, it doesn't matter, either side. Isn't that nice? Because it's secondary, but I'm getting a bump up, or I'm getting a bump in my stability here. I'm doing better stability-wise. Why? There's a reason I'd like to shift over. If you said resonance, you are correct. So there's actually going to be a hydride shift here. The hydride will shift over. The empty seat, so this is the rearrangement step. The empty seat is now secondary, but with resonance. I went from secondary to secondary plus resonance. Way better. Okay, now I'm ready to do my last nucleophilic step. And I changed the nucleophile on you because I thought it was very uninteresting to use water. Let's use ethanol. Ethanol is the solvent. There's tons of it. And it can happen from the front or the back. So I'm going to get a mixture of front OH ethyl and back OH ethyl. And then you have to work those up. You got to take off the extra proton that is making the oxygen positively charged. You can't take off a carbon. You just want to finish this up with some acid-base chemistry to remove that extra proton, neutralize everything, and you're there. So at the end of the day, after we have finished this reactions workup, what you're going to see are two products. And they're ethers. And their relationship, well, they happen to be enantiomers here. This was probably a really tough problem because you have to turn your OH into a better leaving group. So you're adding an extra mechanistic step. It went acid-base chemistry, then solvolysis, formation of the carbocation, rearrangement of the carbocation, that whole thing And then nucleophilic attack from front and backside is all part of the SN1 mechanism. And then you end it with another acid-base reaction. Think about it too. We started the reaction under very acidic conditions, right? And we had those hydrogens, extra hydrogens, because we're under acidic conditions. When you finish the reaction, it's best to neutralize everything. And since we were under H2SO4 conditions, neutralizing it using a base to neutralize all of our H2SO4 that's probably floating around gets us back to neutrality and gives us our neutral ether products, our organic compounds that should be neutral. So you need to take off all those extra protons by equilibrating the whole thing, neutralizing the whole system with base. Typically, you can figure out what your workup conditions are based on your starting materials. Like in this case, it was acid, so you're going to end with base to kind of neutralize everything. Take off those extra protons. So acid-base chemistry, SN1, acid-base chemistry. I'll leave the second one for you guys to try. I have a lot of practice here. In this one, you can rank the molecules in order of decreasing reactivity for an SN1 reaction, ranking the fastest with 1. I have more practice here, which alkyl halide would be more reactive in an SN2 reaction. And then you can go back and reconsider them. Well, which one would be more reactive in an SN1 reaction? Which alkyl halide would you expect to be more reactive in an SN1 solvolysis reaction? So you only have to consider the solvolysis portion and explain your reasons. So let's summarize what we've looked at here. We have covered 2 very important mechanisms in organic chemistry: substitution nucleophilic reactions, or SN1 and SN2. I want to summarize their differences in one chart to kind of make it a little bit easier to see the differences and the nuances. Let's start with leaving group. Because we're working with alkyl halides as a functional group, a good leaving group is necessary for both of them, and they have the same trends for leaving groups, right? Iodine is a better leaving group than bromine is better than chlorine. So we see that. That's the same. That's the only thing that looks the same. Nucleophile-wise, right, in the nucleophile category, SN2 tends to use strong nucleophiles. They're not always negatively charged, but I'd say 90% plus of the time they are going to be. One example of non-negative, formal negative charges that do undergo SN2 are amines. Remember, amines are those nitrogens are so generous that they don't actually need to be negative in order to undergo an SN2 reaction. So I just want you to be aware that amines don't need to be in their negative form in order to undergo SN2, but everything else pretty much does. SN1, weak nucleophiles, we're talking about partial negative charges, or negative charges that are so stable, because of resonance and whatnot, that even though they have a negative charge, they're actually on the weak side. But for 90% plus of the time, SN1, you're going to see the solvent also acting as the nucleophile, and the solvent will be a neutral species: ethanol, methanol, water, right? Things like that, or any alcohol. Now, the alkyl halide, or the substrate, the electrophile, I should say, right? So this is the electrophile bearing the leaving group. We see the exact reverse trends for SN1 versus SN2. SN1, we want tertiary. That's what we're aiming for. Tertiary happens much faster than secondary, but in SN2, it's all about stereochemicals. A methyl is better than a primary, is better than a secondary, and we don't even think we can do it. So SN2, it's like you can kind of avoid tertiary. Those aren't going to really react SN2, but in SN1, you kind of want to avoid primary or methyls. Solvent systems, well, we need to use aprotic solvent systems in SN2. Acetone and DMF and DMSO. We want there to be polarities because we've got to dissolve stuff, but we can't let it be strongly polar with a proton because it'll just tie up our nucleophile and slow things down. Protic systems are desirable for SN1 because those are the ones that help stabilize the emptiness and also help carry away the leaving group. Rearrangements. Rearrangements are impossible for SN2. Impossible. We don't even have to consider them because you're in and out and you're done. It's a fast mechanism, concerted. They're backside attacks, so you just don't even have to worry about anything happening in between because it's just, there's no intermediate. It's just a transition state, one and done. While SN1, you got to stop, right? They're common. SN1, you got to add that extra step, the stop sign at the second step, and look around. Make sure that you've got the best carbocation you have. If not, you've got to consider a hydride or an alkyl shift. Stereochemistry, SN2, you're going to invert the stereocenter. So if you had a bromine in the back, your nucleophile comes in from the front, and vice versa. You're only going to get an inverted stereocenter. SN1 is going to mix that stereocenter. Does it mix all stereocenters in the molecule? No, just the one that's undergoing SN1. So be mindful of that when you're doing the problems. So we have covered acid-base chemistry. We have covered radical chemistry. We have now covered both SN2 and SN1 chemistry. We're slowly ticking the boxes here for mechanistic motifs. We're going to be looking at very shortly, oops, and I checked the wrong one, SN1. We're going to be looking at very shortly E1 and E2. This is the next place we're going, okay? And we'll probably end the semester with the pi nucleophile, pi base reactions, along with Syn3 and Syn4. So at the end of Orgo 1, the yellows and the green checks are what we will have covered mechanistically. And the 1, 2, and 1, 4 additions are what we're covering all of second semester. And we'll still see the others, of course. And once you learn them, we're going to use them. So learn them, practice them. Practice your arrow pushing, and then practice, again, don't get hard on yourself. You're not supposed to look at a reaction and automatically know what the products are. This is your key to working out your answer, okay? Work it out like a math problem. Don't expect to just spit out some product mixture answer. That's not how it works. I can't even do that. I have to sit with pen and paper and slowly do the mechanism, count my carbons, make sure I didn't drop any from, drawing it from one to the next, and figure out what my mixture is going to be. And then I can step back and look and analyze and say, ooh, if I get a mixture of products, can I separate those in the lab? What's their relationship? This is what we've been training you for. So this is what you need to do.